You've definitely seen this image before, that fiery orange ring, the first ever picture of a black hole burning away at the center of the M87 galaxy. It's truly one of the most incredible scientific achievements of our lifetime. But here's the thing. This isn't a photo in the way you might think. It wasn't just point and shoot. It was built piece by piece. So the real story here isn't just what we saw, but how on Earth we managed to see it. And that's really the core question we're digging into here. I mean, the final image is absolutely spectacular, but it's the end result of solving one of the most gigantic data challenges in the history of astronomy. This is a story about how you find a tiny whisper of a signal inside a hurricane of pure noise. So first off, you've got to understand just how insane the scale of this problem was. The M87 black hole is 55 million light-years away. Trying to get a picture of it from Earth, well, that's like trying to photograph a single orange sitting on the surface of the moon. The amount of detail, the resolution you'd need is just mind-boggling. And that is exactly why this was so historic. This quote, it's from the actual scientific paper, and it captures the breakthrough perfectly. For the very first time, scientists had the tools to actually see the structure right at the edge of a black hole, the point of no return, the event horizon. So how in the world did they build a tool powerful enough to actually do it? Well, before we even get to the telescope, let's talk about the data. In just 1 week of looking at the sky, this project generated 5 petabytes of raw data. That's 5,000 terabytes. We're not talking about a file you can email. We're talking about a literal mountain of hard drives that was so huge they couldn't even send it over the internet. They had to fly the hard drives around the world on airplanes. And this entire data storm would eventually be crushed down into that single iconic image. Right, so to get the kind of resolution you need to see that orange on the moon, you would need a telescope the size of a planet. And that's pretty much exactly what the Event Horizon Telescope, or EHT, is. It's not just one big telescope, but a whole network of them, spread across the globe, all working together as one giant eye. The technique that makes it all possible is pure genius. It's a technique called Very Long Baseline Interferometry, or VLBI for short. The basic idea is actually kind of simple, even if doing it is incredibly hard. But using atomic clocks to perfectly time when a radio wave hits different telescopes that are thousands of miles apart, you can combine their signals. The distance between any two telescopes, that's the baseline, is what gives you your resolution. So with telescopes all over the planet, you get a virtual telescope lens as wide as the Earth itself. And just look at this map. You can really see the sheer scale of this operation. This isn't one lab. It's a planet-wide team effort. Each one of those yellow dots is a telescope site, and the blue lines connecting them are those baselines we were just talking about. Every single line is like a pair of eyes contributing a unique piece of the puzzle, all to build that final sharp picture. This was truly a global human achievement. You have teams in the bone-dry Atacama Desert in Chile, on top of volcanic peaks in Mexico and Hawaii, in the mountains of Arizona and Spain, and even, believe it or not, at the actual South Pole. Every one of these places had to be synced up perfectly to catch the exact same faint radio waves from 55 million light-years away. Okay, so the team built their planet-sized telescope. They collected the petabytes of data. Amazing. But here's the catch. That data was an absolute total mess. The real signal from the black hole was completely buried under a massive wall of noise and distortion. You see, collecting all that data, that was just the first battle. Cleaning it, that was the real war. The first enemy was our own planet's atmosphere. You know how heat haze makes the road shimmer on a hot day? Well, water vapor and turbulence in the air do something similar to radio waves, creating this constant blurring effect. And it had to be corrected for every single telescope for every single second of observation. And then there was the telescope array itself. The paper calls it highly heterogeneous, which is a fancy way of saying they were all different. It was a motley crew of instruments, some single dishes, some arrays, all with different electronics and sensitivities. Trying to get them all to speak the same language was just a monumental task. And this, right here, is maybe the most mind-blowing part. In the raw data they had, the signal from the black hole was completely gone, undetectable. It was literally lost in the static. It was only after a ridiculously painstaking multi-step calibration process that the tiny whisper from the black hole could finally start to be heard over the roar of the noise. So how do you trust a signal that you have to dig out from that much noise? How do you know you're not just fooling yourself? Well, you check your work. And then you have 2 other completely independent teams check it all over again from scratch. This was the absolute key to their success, a super rigorous triple-check system. To make absolutely sure that the final image wasn't just some fluke of their computer code, the EHT team developed 3 totally separate, independent data processing pipelines. You can think of it as the ultimate scientific safety net. If all 3 completely different methods came up with a similar result, then and only then could they be confident that it was real. So they formed 3 different teams. Each one used a different set of well-established astronomy software, and crucially, they worked in complete isolation from one another. They were all handed the same raw, messy data and told, go find the signal. It's just an incredible example of doing science the right way. To put it simply, the whole process really boiled down to 3 main stages. First, correlation. That's where they use those atomic clocks to sync up the petabytes of data from all the different sites. Then came the 2 really critical steps, phase and amplitude calibration. Let's think of it this way. Phase calibration is all about syncing the signals. It's like lining up sound waves from a bunch of microphones so they work together instead of canceling each other out. This is what fixes that atmospheric blur. Then, amplitude calibration is like equalizing the volume. It adjusts for the fact that some telescopes are naturally more sensitive than others, putting all the data onto the same universal scale. And after pushing all that raw data through these intense triple-checked pipelines, something truly incredible happened. The noise just fell away. And out of that chaos, a clear, coherent signal started to emerge. Now, this wasn't the image yet. It was something even more fundamental. And it's so important to understand this. Before you can even think about making a picture, you need this, a clean, calibrated data set of what scientists call visibilities. This final, refined data is the real scientific prize. It's the purified essence of the black hole's signal, from which all the images and the models are actually born. So what did they find in that clean data? They saw a clear, repeating pattern. Specifically, they found 2 sharp dips in the signal's brightness at very particular distances between the telescopes. This wasn't random noise. It was a structured, consistent signature. This pattern is the unmistakable fingerprint of a bright ring of light surrounding a dark shadow, the direct evidence of the event horizon found right there in the data, long before a single pixel of the final image was ever created. So in the end, that amazing image of the black hole was the grand prize. But the real breakthrough was learning how to listen for its tiny whisper in a cosmic storm of noise. This cleaned up data was the key. And it just makes you wonder, right? What other incredible secrets about our universe are still hiding out there, buried in the noise, just waiting for us to figure out a clever new way to listen?